For pretty much all of human history, we've looked up at the sky and seen this breathtaking, mysterious, beautiful dance of light, the aurora. It's without a doubt one of the most spectacular shows on Earth. But you know, behind all that magic, there is some truly incredible science at play.
So what is actually going on up there? I mean, what kind of cosmic engine is powerful enough to paint the entire night sky with curtains of light? Well, to figure that out, we've got to trace this whole performance all the way back to its source.
And believe it or not, our story doesn't start here, on a cold polar night. Nope, it begins 93 million miles away, at the very heart of our solar system, with our sun.
The engine for this whole thing is something called the solar wind. And look, this is no gentle breeze. We're talking about a super high-speed flow of energized particles, constantly blasting away from the sun's fiery outer atmosphere. This stream is the fuel for the entire light show.
So the first part of this journey is just getting those particles from the sun to us. The sun kicks them out into space, they travel for a few days, and then, bam! They finally reach Earth, and they slam right into our planet's first line of defense.
And that brings us to the real unsung hero of this story, Earth's magnetic field. Seriously, without this thing, life as we know it probably wouldn't exist, and neither would the aurora.
The easiest way to think about the magnetosphere is as this giant, invisible bubble surrounding our planet. It's generated by Earth's core, and its main job is to deflect that constant, dangerous barrage of solar wind, basically protecting our atmosphere from being stripped away.
Okay, but here's the cool part. The shield doesn't block everything. The solar wind is so powerful that it actually squishes and stretches this magnetic bubble out. And that distortion is absolutely key, because it lets the magnetosphere catch some of those solar particles and funnel them down along magnetic field lines, steering them directly toward the north and south poles.
And that's why we get two light shows. We've got the Aurora Borealis in the north and the Aurora Australis in the south. What's really wild is that they're often almost perfect mirror images of each other, happening at the exact same time at opposite ends of the world.
So these captured particles are now racing down those magnetic highways toward their final destination. High above the Earth, we're talking over 80 kilometers up, they're getting ready for the grand finale, a massive high-speed collision with the gases in our atmosphere.
And this is where the magic really happens. It's those high-energy collisions that create the unbelievable light show that we see from the ground. It's just beautiful physics. A solar particle comes screaming in and smacks into an atom in our atmosphere. It transfers its energy to that atom, basically giving it a jolt and kicking it into an excited state. But things don't stay excited forever. To calm back down, the atom has to release that extra energy. And it does so by spitting out a tiny particle of light, a photon.
Now, the color of that light tells you exactly what's going on. It all depends on which gas got hit and how high up it happened. So when you see that brilliant common green color, that's oxygen getting excited at a lower altitude. But if oxygen gets hit way up high, you get those rare, beautiful reds. And nitrogen? That's what's responsible for the blues and purples you sometimes see at the bottom edge of the curtains.
And the magnetic field doesn't just guide the particles, it also sculpts the light into all these different shapes. You know, sometimes it's just a faint glow on the horizon. Other times it's a huge sweeping arc across the sky, or shimmering rays of light shooting straight up. And during the most intense displays, you might even see a corona, where it looks like the light is literally exploding from a single point right above your head. It's spectacular.
So, as you can see, the aurora is way more than just a pretty sight. It's a visible, tangible link between our planet and the sun, a connection that has fascinated and even directly impacted people for thousands of years. It's amazing how our understanding has changed. I mean, we've gone from ancient legends to Galileo finally giving it a scientific name, to that massive discovery in the 1800s linking it to the sun's activity, and then, finally, in the space age, we just sent rockets right up into an aurora and proved, once and for all, that it was caused by electrons from space. But before all the science, there was folklore, and you can totally see why. The Chippewa Dene people, for instance, saw those dancing lights and believed they were the happy spirits of their ancestors dancing in the sky. What a beautiful way to explain something so mysterious.
But there is a flip side to all this beauty. The lights are a sign of an immense amount of energy being poured into our planet's system,
And when a really, really powerful blast from the sun hits us, it creates what's called a geomagnetic storm, and the effects of that can be felt right down here on the ground.
And the ultimate example of this is the Carrington event of 1859. This solar superstorm was so incredibly powerful that the northern lights were seen as far south as the Caribbean. Imagine that! It was beautiful for sure, but it was also a terrifying display of raw power. The storm actually induced so much electricity in telegraph wires that they started sparking and setting fires. And get this, some operators, in a moment of pure genius, disconnected their batteries and found they could send messages using only the raw power generated by the aurora itself. Can you imagine that? They were pulling electricity right out of the sky.
Okay, so let's put it all together. It starts with the solar wind from the sun. Earth's magnetic field grabs those particles and funnels them to the poles. They smash into our atmosphere, and that collision creates the light we see. The different colors tell us which gases are getting hit, and a really intense aurora is a sign of a powerful geomagnetic storm. A reminder that this beautiful show is connected to some serious power.
And that leaves us with one last pretty critical question. Back in 1859, that storm messed with the most advanced tech of the day, the telegraph. So if another Carrington event hit our modern world of satellites, power grids, and the internet, what would happen then? It's a pretty sobering thought, isn't it? A reminder that the greatest light show on Earth is tied to one of the greatest forces in our solar system.